Today is the last class of your postgraduate diploma in analytical chemistry program, and today we will discuss the left out part of yesterday's unit 12 and followed by the unit 13, and which are very much related to your radiochemistry or radioactivity, or it is also known as nuclear chemistry, because this is deals with the some phenomenon of nucleus or nuclear changes happen due to disintegration. So now I am sharing my screen with you. Is this visible, students? Radioactivity.
Yes, sir.
Okay,
Yes,
thank you,
sir.
thank you. So all are requested to mute, and on behalf of my side and from IGNO Regional Center Bhubaneswar, I welcome you all to this online platform conducted by IGNO RC Bhubaneswar, the theory classes of your PGDSC program. And today we will have the radioactivity part of your paper MCH-004. It is the last paper. That is block 5, last block, and the penultimate unit, that is unit 12, and also unit 13 is there. And so let's discuss from the starting. That is it is nuclear radiation or nuclear chemistry. It is the study of structure of atomic nuclei, as pointed out yesterday, that according to the Rutherford's gold foil experiment, and he concluded that every atom is consist of two parts, nuclear part and extranuclear part. The nuclear part is consist of proton and neutrons, and which bear the whole mass of an atom, and in the extranuclear part electrons are revolving around the nucleus like planets are revolving around the sun. So how these protons and neutrons bearing the same charge are um, are placed in a compact space in the nucleus. So from this query, there is a concept arise that is known as a nuclear force. So this nuclear force is a very strong force which bind the protons and neutrons present inside the nucleus. So from this we have some structure of atomic nuclei study, and in the next part we will have what are the changes they undergo. So this is the discovery of radioactivity. It was first observed by William Röntgen in 1923. Sorry, 1845 to 1923 his period, and he discovered these things in 1895. And he observed invisible rays are coming out from certain materials when bombarded with electrons. And after that, he also observed photographic plates to be darkened due to this effect, and he named this invisible high energy emission as X-rays. And this concept was moved forward by the great scientist Henry Becquerel, whose period is 1852 to 1908, and he was studied the concept of phosphorescence. So when he studied the concept of phosphorescence, he observed some minerals emit light after being exposed to sunlight. Like this is the picture. Some material emits some light when it is exposed to sunlight. So this phosphorescent uranium salt produced spontaneous emission that darkened photographic plate. So this is a photographic plate. So when uranium metal is exposed to sunlight, so this photographic plate darkens. Then he concluded that some high energetic rays are coming out from this uranium metal when exposed in sunlight, and this is a new concept in science, and he named this as radioactivity. Then we have, and this work of radioactivity was moved forward by the great scientist from Poland, and she is none other than Marie Curie, and her period is 1867 to 1934, and uh, she with her husband Pierre Curie, 1859 to 1906, took Becquerel's mineral sample, that is pitch blende, and isolate the components emitting the rays. So both are working on this radioactivity concept, and for their contribution towards science, that first they combiningly discovered the element that is radium, for which they both got Nobel Prize in Physics. Then after her husband's death, Marie Curie's death, Marie Curie single-handedly discovered the element polonium. So she named this new element as polonium because it belongs to Poland. So also she died due to the bad effect of radioactivity or radioactive materials, because these are very harmful and hazardous to our health, and this generally causes tumor or cancer in our body. So she is the only human being or only woman in the world till now who got two Nobel Prizes. First one with her husband uh, in physics, and later on she awarded with Nobel Prize for the discovery of polonium in the field of chemistry. So darkening of the photographic plate was due to rays emitted specifically on the uranium atom present in the mineral samples. So then Madame Curie named process by which materials give off such rays radioactivity. The rays and particles emitted by a radioactive source are called radiation. In type of radiation we have alpha radiation, beta radiation, gamma radiation, depending upon the type of isotope. So isotopes are atoms of the same element that have different number of neutrons. That is same atomic number but different mass number. So when mass number varies, the number of neutron varies. When isotopes are unstable, these are called radioisotopes. Like carbon, carbon has three isotopes: C612, C613, and C614. And between these three, C613 is the most radioactive because this isotope is very unstable. Emit radiation to attain more stable atomic configuration, a process called radioactive decay or radio disintegration. So due to radioactive decay, there will be energy loss by emitting one or more several radiations. That is radiations in the form of alpha ray, beta ray, or gamma ray. So why some atom decays? So when the neutron to proton ratio, okay, because nuclei contain tightly packed proton and neutrons in a compact area. Proton and neutrons are there, but in spite of the same charge, there will be force of repulsion. So after that also, these subatomic particles remain in the nucleus without affecting any stability to the atom. So this is possible due to the nuclear force, which is a strong force, and it is an attractive force. So here it is written: the strong nuclear force keeps the nucleons. Nucleons means it is proton and neutron, both are called nucleons, packed together even though protons want to push each other out. That is, the force of repulsion arises due to same charge protons. Still, they are kept in the same nucleus due to strong nuclear force. So when the neutron to proton ratio is 1 is to 1, this is very stable, like C612, where number of proton is 6, number of neutron is 6. So C612 is exceptionally stable. But C613, it becomes radioactive or relatively unstable. So due to N by P ratio is not 1 is to 1. As atomic number increases, more neutrons are required to have enough for a strong force to keep the proton pushed together. Neutron to proton ratio for stable atoms increase to 1 is to 5. 1 is to 5.1 is to 5. 1.5 is to 1. That means when number of neutron gradually increases, the number of proton um, is unity, that is 1.5 is to 1. When this ratio, up to this ratio, the nuclei is said to be stable. When this ratio increased 1 is to 5 is to 1, when it is greater than this, the nuclei is said to be unstable. And this is the band of stability, where number of proton neutrons are plotted, the stable nuclei are found within the band of stability. That is the band of stability when it is n by p ratio is 1.0. And when radioisotopes are outside the band of stability, these are the radioisotopes which are outside the. Is this visible, students? Band of stability?
Yes, sir.
Okay, okay.
Yes, sir.
So when the n by p ratio is 1.0, that is neutron to proton ratio is 1.0, these nuclei are exceptionally stable. But when the ratio is maximum 1.5, so these nuclei are said to be radioactive, and they will undergo nuclear reaction to become more stable, because these are relatively unstable, and they are unstable due to the imbalancing of number of proton and neutrons. That's why they are undergo nuclear reaction, that is a reaction of the nucleus to become stable. All elements higher than atomic number 83 are radioactive. This is in general, that above 83 atomic number, above it, all the elements are radioactive, that is, they are relatively unstable. And this is the same band stability. We have n equal to z here, that means it is 1 is to 1. And when this ratio is increased up to 1 is to 5, then we have some nuclei with this region, that is number of neutron is let us number of neutron is around 85, right? And number, atomic number here, that is number of proton, it is around 85 or 83. It is undergo alpha emission, and the neutron number is around 60 or 62, and it is atomic number is just like your 30 or 35. Then up to the above this we have also the beta emission. This is just an example of your band stability. Then we have type of nuclear radiation, as point out yesterday's class. There are primarily of three types of radioactive rays which are coming out from unstable radioactive nuclei. These are alpha ray, beta ray, and gamma rays. Alpha ray is same as the helium nucleus, that is He24. Beta ray is same as electron, E minus 1 0, and gamma ray is about Y00, that no mass and no charge. Then it is written here, the alpha radiation, it is charge 2 plus and mass is 4 atomic mass unit, and this is equivalent to helium nucleus. So these have 2 proton and 2 neutron. The largest, and this is the and this radiation or this ray mass is 4 atomic mass unit. This is the heaviest ray between these three, that is alpha, beta, gamma. So between these three rays, alpha is least penetrating and can be stopped by a single paper also. So this is alpha because these are the highest mass, 4 atomic mass unit. Changes to a different element with a lower atomic number and lower atomic mass. Example is polonium, that is 212 atomic mass with atomic number 84. It would be converted if it polonium is radiate alpha ray, then the mass number will decrease by 2, and the atomic number is, sorry, then the atomic number is decreased by 2, and the mass number will decrease by 4, because alpha ray is same as the helium nucleus. Then this is alpha, this is plutonium 94 240. Then when alpha ray is emitted, then what happens? The 94 becomes 92 and 240 becomes 236. So which element has the atomic number 92? It is uranium. That means plutonium is changed to uranium by the release of alpha particle. Then beta is same as electron, that is E minus 1 0. That means it is after beta radiation emission, what happens? The atomic number will increase by 1 unit, and the mass number remain constant. So this is the example, that is cesium 55 137. If electron or beta particle is emitted, what happens? The 55 becomes 26, because this is E minus 1 0. So 55 becomes 56, but the mass number remains constant, 137. Another example, if sodium 1122 radioactive, if it emit one electron, what happens? This 11 becomes 12. No, no, no. This is wrongly written here. Sorry, this is emission of electron, but this is emission of positron. Positron is also a radioactive particle that may be emitted from a nucleus. This is just the reverse of electron. This is beta ray, but this is positron. So if a beta particle is having minus 1 charge, then this is electron. If beta particle having plus 1 charge, is it known as positron. If positron is there, there will be loss of proton by 1 unit, and the mass remain constant. So this is sodium 11 becomes a neon 10, and 22 mass remain constant. So this is electron, this is positron. Both are different and both are just opposite to each other. Then we have gamma ray. This is not a particle, this is just an energetic ray with short wavelength and high frequency and energy, no mass, no charge, very fast and speed of, that is speed of light, stronger than X-ray, stopped by several centimeters of light. So this is the just the gamma. This is X-ray and this is the gamma ray. These are very much complementary to each other. So if I go for the penetration power, that alpha ray, that is have the highest value of your mass, it can be stopped by a paper. So followed by the beta ray, which is electron or positron, it can be stopped by a aluminum foil, okay, or aluminum sheet. Then gamma rays can be stopped with lead or concrete. So these are very much having the highest penetration power, followed by beta and alpha. Then transmutation is changing of one element, a radioactive element, into another. This is known as transmutation. That is adding or removing a proton, change the atomic number, resulting in a different element. For half-life, these are also discussed by yesterday. That is half-life period is the time period at which half of the radioactive nuclei are reacted. So this time period is known as half-life period. And as this disintegration of nuclei, that is radioactive disintegration nuclei, obeys fast order kinetics. So that's why here lambda is the disintegration constant, right? Like your rate constant, lambda equal to 2.303 by t log log n by n0, where capital N is your number of nuclei left after disintegration, and n0 will be the initial number of nuclei. So these things are there. Half life period will be 0.693 by lambda. So this is transmutation, that is potassium, then argon, then calcium. So this is the conversion of your from potassium to calcium by radioactive phenomenon. And this type of changing of element by nuclear reaction or radioactive reaction is known as your transmutation, having different half lives. That is having and this part is having half life 1.3, this is 2.6, and so on. This is the half life equation. Mf equal to mi half per n, where mf is your final mass, mi is the initial mass, and number of n is the number of half lives. Then nuclear decay. So it is better to have our PDF discussion from here. This one. And yesterday we have discussed up to your half-life period. Let's have the two types of radioactivity: the natural radioactivity and artificial radioactivity. So natural radioactivity, we have some series are there that will involve the emission of alpha, beta, and gamma rays. So this is the series of 4n plus 3. That is from uranium 235. There will be a series of changes of the nuclei, and at the end we have lead 20782 atom 82207. So uranium 235 emit alpha ray converted to thorium, emit beta ray, praseodymium, emit alpha ray again, actinium. Then it can have two ways now. It can radiate alpha ray or either beta ray. If it is alpha ray, the series will be francium, astatine, bismuth, polonium, lead, bismuth, thulium, lead. Then if it is beta, thorium, radium, radon, polonium, astatine, bismuth, polonium, followed by lead. So this is the series of 4n plus 3. So 235. This is 235 means it is undergoes 4n plus 3. How it is 4n plus 3? If I subtract 3, it will be just to know which series this conversion belongs, just divide the mass, that is 235, with 4. So if I divide 235 with 4, see here, if I divide 235 with 4, is 8.75. That means it is 58 and the remainder will be 3. Okay, so that means it is 4n plus 3. So by this way, you will know that in this series this conversion belongs. So with 4n plus 3. Sir, voice is not clear, Chandini sir. So am I audible, students, or any problem in listening my voice?
Yes, sir, audible, but voice is not clear, sir.
Not clear. Okay. Now I am audible.
Yes, sir.
Yes, sir.
Okay. So I asked to Chandini. Chandini, is my voice is audible to you, Chandini Sahu?
Yes, sir. Now is audible.
Okay, thank you. So, from this simple calculation, you will able to detect to which series this conversion belongs. That is simply just divide the atomic mass, that is the mass number, with 4, and if the remainder will be the plus part, that is 4n plus 3. Similarly, we have the 4n plus 2 series. If I divide 238 with 4, just see, 238 with 4, 238 divided by 4 will be 59, the remainder will be 2. So the series is 4n plus 2 series. So what are the conversion? Uranium 238 emit alpha to thorium, beta to praseodymium, beta to uranium, again thorium, again radon, then radium, radon, polonium, lead, bismuth, thulium, lead, mercury, thulium, bismuth, polonium. Then at the end we have lead 82206. So this is 4n plus 2. Then the, the series came 4n series, that means 232 series. So if I divide 232 with 4, the remainder will be 0. The remainder is 0. That means this series is your 4n series. Okay. So by this way, you can you will know that to which series this conversion belongs. Then classification nuclide, the same thing, stable nuclide, that have a neutron to proton ratio equal to 1, and there are 275 such nuclides are there. Then primary natural radionuclides are found in nature since origin of the solar system. They have the long half lives, like uranium having half life 4.5 into 9 years, potassium 40 1.3 into 10 to 9 years, rubidium 87, it is 4.5 into 9 years. So these are naturally occurring radioactive nuclides having the long half lives. Then secondary natural radionuclides, such as half-life period are very short, that is radium, thorium, they have the short half-lives, like thorium is 24.1 day, radium is 1600 years. So like this. So induced means it is induced natural radionuclide means it is by the action of cosmic rays. For example, we have tritium H13, it is 12.3 year, and you have carbon 14, it is 5730 year, and this carbon 14 isotope, this is used in carbon dating. What is carbon dating? To determine the age of old samples, that is age of a tree, age of a mummy, or age of a historical thing that is collected from different sources. So by carbon dating process, we are determining the age of that old species. Then artificial nuclear radionuclide, this is artificial. So till now 2000 such nuclides are invented, and this will be discussed in the next section. Then we have isotope, isobar. These things you all are known. That is, isotope is all about same mass, same atomic number, different mass number. That is, number of neutrons are different. And the isobar is different atomic number but same mass number. Like boron 12, carbon 12, N12. So these have the number of proton 5, 6, 7, but they have the same mass number 12, 12, 12. So this is 4n plus 1 series, that is neptunium to bismuth, and this is the conversion, that is neptunium to praseodymium followed by uranium, thorium. This is radium, actinium, francium, astatine, bismuth, thulium, lead, or from bismuth to polonium, lead and then bismuth. So this type of conversion including on 4n plus 1 series. Then we have isotones, that is another type of or another category of nuclide which have the same number of neutrons. This is known as isotones. Like C614, the number of neutron is 8. 14 minus 6, it is 8. It is N715, the number of neutron is also 8. If it is oxygen 816, the number of neutron is 8. But that means when the number of neutron is same for different species, the different species are known as isotones. So we have three types of nucleides are there. One is isotope with the same atomic number, different mass number. One is isobar, that is mass number is same, atomic number is different, and the third part is your isotone. Then nuclear isomers are there, like your um, for example is your bromine 80m, bromine 80. So the indicator one isomer is a nuclear excited state with a different half-life. That means these are the two nuclear isomers having different half-life period. So isotopic and radioactive relative atomic masses. So if I convert one atomic mass unit, that is 1 U, to uh, to the respective weight, that will be 1.66 into 10 power minus 24 gram. So how it is calculated? So it is equal to 1 gram per mole divided by Avogadro's number. This will be 1.66 10 power minus 24 gram. If I convert this gram to kg, it will be minus 27 kg. And by converting this much weight to corresponding energy by using Einstein's mass energy equation, that is mc square, and if I multiply this with c square, that is 3 into 10 to the power 8 meter per second square, then the net energy generated will be 931.5 mega electron volt. That is into 10 to the power 6. Mega means million, okay. So 931.5 mega electron volt. That means one atomic mass unit, this is very minute mass, 1 U. It is equivalent to 931.5 mega electron volt energy. So that you should think that how much energy will be produced by a heavy nuclear atom or heavy nuclei when it is undergo nuclear fission or fusion reaction. And if I convert the mass of sodium, it will be 23.190036 atomic mass unit. And if I convert these to their respective energy, then I will multiply this mu with your this mu with first 1.6 minus 27 gram into 931.5 MeV, and the net will be your huge amount of energy will be liberated. Okay, so these things will be there. Then artificial radioactivity. This was first given by the Ernst Rutherford. That is, he bombarded nitrogen 14 with alpha ray, and he alpha ray. The products are oxygen 817 and water. Like the second artificial was aluminum 1327 bombarded with helium, that is alpha ray. It will give phosphorus 30 with one neutron N01. Then we have nuclear reactions, and this is the general nuclear reaction representation. That is uh, the radioisotope T with atomic number Z1, mass number A1, is bombarded with high energetic radioactive particle or high energetic subatomic particle with atomic number Z1 dash and mass number A1 dash. The product will be PZ2A2 plus E, that is the secondary particle which is liberated with atomic number Z2 dash and mass number A2 dash. And here you should remember that Z1 plus Z1 dash equal to Z2 plus Z2 dash, and A1 plus A1 dash equal to A2 plus A2 dash. It is written here Z1 plus Z1 dash equal to Z2 plus Z2 dash, and A1 plus A1 dash equal to A2 plus A2 dash. So you have to just see, there is simple calculation that that number of subatomic or radioactive rays which are produced by this nuclear reaction. Then we have, let us this one, chlorine 35N. What is in the fill in the blanks? Plus Y. That means what will be the answer here? It is chlorine 1735. Neutron is N01. That means the total atomic number is 17 plus 0. It is 17. It is 35 plus 1 means it is 36. So it is Y00. That means here what happened? If chlorine is bombarded with neutron, then the product will be again the chlorine 17, and the mass is changed, that is 36, because by the with the um, with the liberation of the gamma ray, there will be no change in atomic number, and there will be unit atomic mass will be increased. So 35 becomes 36, and close the atomic number as this becomes the same. That's why the element is also same. This chlorine. Then we have just see here the calculate Q. Q means it is the amount of energy. So how to calculate it? Aluminium, its actual mass is 26.98, and helium, that is 4.002. And this is the equation, that is when aluminium is bombarded with deuterium, that is H12, that will be liberated, that is magnesium will be liberated. Magnesium is the product with alpha ray. So what is the mass of the reactant? This is 26.98 something of the aluminium plus deuterium 2.01. It will be net will be 28.this, and for magnesium it is 24, and for helium it is 4.00. The net is 28.98. What is the mass difference? The 28.955 minus 28.988 into 935 931.5 MeV. So this will be 6.701 mega electron energy. That is when aluminum is converted to magnesium by d alpha disintegration, we have 6.707 of mega electron volt energy loss. So this is the same way you can calculate. Then we have have these things. It is also very easy that the aluminium bombarded with neutron, if it release gamma particle, the aluminium remains the same. Aluminium is aluminium, but the mass number increase 28. If it is neutron and proton, it is magnesium. If it is neutron, that is N means it is neutron, alpha means it is at the product side, and N is at the reactant side. If it is alpha, then the mass atom number will be decreased by 2, it is sodium. If it is 2 numbers of neutron, then it is the atomic the atomic the number remains same, and this will be again the aluminum. So these things are there, and this is the activity equation, that is n phi sigma t equal to wi by m phi sigma t. And this commonly used radioisotope, these are the radioisotopes which are commonly used. These are the type of radiation which is make this unstable isotope to a stable form with their half-life periods are here, and what are the amount of energy in kilo electron volt, these are mentioned here. Then at the end we have preparation of radioisotope and repelled compound. So this concept was given in 1913 by George D. von Hevesy, and he obtained lead 82 210 isotope from uranium decay series. And then we have detection of measurement of radioactivity. This is an experimental view of your radioactivity, that is how experimentally we can detect, and how we can detect the strength of radioactivity, what is the measurement. And the detection of nuclear radiation emitted by radioisotope depends on the type of radiation and its energy and the nature of material which they interact, and what rays it is irradiated, and what subatomic particle it is liberated. So this type of these are the factors on which this detection and measurement depends. And we have there must be strict proportionality between number of proton and particles interacting with the detector and the number of pulses generated. There must be linear relationship between energy of radiation and the amplitude of the voltage pulse, that is pulse side. So this we have three types of detectors, that is gas ionization, scintillation chamber or detector, and solid state semiconductor. We have three types of. In gas ionization, what happen, there will be gases will be there which undergo the ionization, and this will be detected through sensors. This is very simple. So just see this instrumentation part of your gas ionization chamber. Then we have some radioactive sources, okay, from where radioactive rays are emitted. So this is the sample container. This is a thin window. The anode wire is there, which is connected to external circuit, and then we have amplifiers, series of amplifiers, mini amplifier, then connected to amplifier, then discriminator, analyzer, then timer counter. So these things are very much well connected, and this is the gas ionization chamber. So this detector consists of cylindrical tube filled with non-conducting inert gas such as argon or xenon, and a central wire acting as anode. This is anode. Metallic wall of cylindrical tube acts as cathode. This is cathode, and this wire is anode. A typical detector system together with its associated electronics is shown in 12.7 figure. When ionizing nuclear radiation passes through this window and interact with gas producing ion pair are collected by the respective electrodes, a voltage pulse is produced which is measured. So when this radioactive rays disintegrate the radioactive nuclei, what happens, there will be change in, there will be interact this will be interact with the gas producing ion pair, ions are collected by the respective electrodes. So this will disintegrate, and then there will be release of ions which will be sensed by the respective electrodes and followed by this series of sensors. So we have a plot here that is applied voltage versus pulse height, and these are the things. This is the voltage that is V1, pulse voltage that is V1, V5. Then we have current voltage curve here, and this is the ion chamber, proportional region of recombination, region of proportionality, major molar chamber, discharge region. So this is the type of different type of this is radioactive detection. Then we have ionization chamber, proportional counter, and geyser molar counter. These things, geyser molar counter, proportional chamber, and ion chamber. So these three, and they are into syllabus. So in ionization chamber detector already we have discussed that one. This is from voltage 0 to V1. This is the region of energy ion recombination part is there, and then we have in GM counter, that is geyser molar counter. We have from the C here geyser molar counter. It is from V4 to V5, and in the discharge and in the proportional counter we have V2 to V3. So depending upon the voltage, we will have different types of radioactive determination. Then we have this is an example of GM countering system, and where the voltage is from 1800 to 2400. This is a working voltage, and there is a plateau here, right? And we will have threshold voltage, that is it will start from 1800, because threshold voltage is the minimum voltage that will be applied to the radioactive substances to have the disintegration, radioactive disintegration. So this is a minimum voltage, and this is different from different radioactive nuclides. But this is known as threshold voltage. This is the starting voltage. So 1800 is the starting voltage in GM counter, and it is goes on, and we have difference in voltage due to the disintegration of radioactive nuclei by the radioactive rays. Then one formula is there, n equal to m by 1 minus m tau, where tau is the dead time of the detector system, and it is the order of 10 to 10 100 to 500 microseconds. It may be determined experimentally. So just read these things, okay? Then a scintillation detector. Then we have in scintillation detector, there will be interaction of nuclear radiation, especially gamma radiation, with the solids, that is phosphor materials, where electronically excited atoms are produced, which in turn can emit light quanta. Light quanta means it is the packet of light. That is light in lighter energy is not in the form of discrete package. It is just a solid packaging, that is known as quanta. The number of light quanta emitted is proportional to energy of the radiation observed, that is related to your Planck's law. That is E equal to h nu. This will be the equation for this quanta concept. Then we have, this is the scintillation chamber, which have the voltage here. This is the optimal coupling, reflector, sample wire. Then we have sodium iodide, thulium scintillator, transparent faceplate. Then we have different types of electrodes. Just go through the instrumentation part. Okay, so this depends on the strength of voltage which is applied to a particular detection. Then photoelectric effect which produce photoelectron of the same energy as that of gamma ray. Then Compton effect, which produces Compton electron, produce a broad peak called continuous gamma spectrum, where a production that is layer greater than 1.02 mega electron volt produces photo peak at 0.51 mega electron volt. And then we have this is a typical gamma rays spectrometer here, which can detect the gamma ray emission from the radioactive rays, radioactive nuclei by department in radioactive rays. And this is percentage of radium from your gamma ray spectrometer. This is FW HM, that means full wave half modulation. Full wave half modulation by peak position in 200. Then we have pulse height analysis, how to measure the height of the pulse. This is the thing. There is a equation here how to measure the pulse height, and this is the plot from our gamma ray detector. Then we have cesium 137 here, which produces 0.66 mega electron volt. Manganese 54, 0.84 mega electron volt. Then we have some equations here. That is net area, total area by C1 to C2. This is the C1 to C2 area minus H1 to H2. This is the height, H1 to H2, and these things are there. And semiconductor detectors, and this is what is semiconductor. This is of two types, that is P type semiconductor and N type semiconductor. So if group 3 element is doped in the group 4, that is the carbon series element, then we will have P type semiconductor, and there will be the free electron will be the conducting part. And when the group 4 element is doping with group 5, there will be a hole is generated, and this hole is responsible for the conduction of electricity, and this is known as N-type semiconductor. So when P and N-type semiconductor are connected, it will give you the PNP transistor. Okay, these things are there. This will be your band theory, or this part is in your solid state chemistry. And then we have some semiconductor of germanium and lithium detector. So this detector, the semiconductor detector, this is used for the detection of gamma ray emission from a radioactive decay. Then we have high purity germanium SPGE detector. This is the advanced version of your semiconductor detector. That is from the top. It is metal housing, SPGE, end cap, FET, and preamplifier. These things are there. Just read these things, and you have a broad knowledge on this. That is the instrumentation part. Then we have at the end we have auxiliary instrumentation, and also there auxiliary means this is the secondary type instrumentation. While using any of the above detector system, auxiliary electronic equipment such as high voltage supply, linear or spectroscopy amplifier, pulse height analyzer, timer, counter, or scalar units are required. The high voltage supply must be of high stability, and amplifier must have high sensitivity. The signal output of a detector is often quite small and is likely to be lost if directly carried through amplifier. Then when the voltage is too much high, there will be the detection will be low due to the heating effect, and the amplifier will lost its sensitivity. So this type of auxiliary instrumentation precaution must be taken, and these modern instruments have displayed and spectra recording facility by connecting it with the digital part, that will be the computer or any digital machines. There will be automatic peak area calculation, calculation of elemental concentration. These things are there in this part. So you have to study the instrumentation part of your gas ionization chamber, GM, the Geiser Muller chamber, then scintillation chamber, then followed by your last one auxiliary instrument. Just read these things. And in the next part of today's session, that will be the last part, and in that part we will discuss some radioanalytical methods. These are very much advanced methods which are used in radioactive decays or radioactive disintegrations, and related to our radioactive rays, radioactive nuclei with some radioactive isotopes. And we will have this part after 5 minutes. So we will exactly meet at 6:35 p.m. So till then, let's have some refreshment. So thank you, students. Till then. So welcome to all.
Yes, sir.
Okay. So we have the last part of your uh, paper MCH-004 of program postgraduate diploma in analytical chemistry, and in the last unit of your paper as well as your program, this is the last unit, radio analytical method. So in this part, uh, these things are also very much new to me also, because in our BSc and MSc level we did not have so much of elaborate discussion, or so much of depth syllabus in our time. So let's have some view on this unit that is related to your radio analytical methods. We have objectives, introduction, followed by radioactive tracers, then how to choose a radio tracer, what are the factors affecting to it, isotope dilution analysis, under this we have principal equation, instrumentation, application, some advantages and limitations. Then we have soft stoichiometric isotope dilution analysis, the SIDA, SIDA. We have activation analysis, AAA. Then principle of nuclear activation analysis, NAA. Then we have some interfaces, sensitivity detection limit, then followed by instrumentation application advantages, comparison between nuclear activation analysis and isotope dilution analysis. Then we have some titration in radiometric. Then at the end we have radio chromatography is also there. There is separation technique. Then radio immunoassay is related to some medical application, and what are the procedures and things are there. Let's have, and these are the things. These are some full forms of your neutron activation analysis: NAA, IDA, RT, RC, RIA. These things are there. What are the objectives are? That is the choice whether it is essential to adopt or not. Describe uniqueness of radioanalytical method. Identify the suitable radioisotope radio tracer. List the suitable radioanalytical method, and these things are there. Okay. So nuclear analytical method, it is broadly of two types: the direct method and indirect method. So let's have the indirect method first. So in the indirect method part, we use of radiation sources that may be scattering analysis, fluorescence measurement, or absorption measurement. So if it is scattering, then it will be Rutherford backscattering, like in Rutherford Goldfoil experiment, that 1 out of 10,000 ray, 1 out of 10,000 ray is coming back to its original axis from where it is originated. So this type of backscattering is in our indirect method. Then beta particle scattering also, it is a scattering, that is backscattering of photon. Then perturbed angular correlation. Perturbed means it is the English meaning is it is disturbed. So perturbed angular correlation. Then we have fluorescence measurement, absorption measurement. We have beta, photon, and neutron absorption. So in direct method, and also you're right, in indirect method we have another part, that is the addition of radio tracer here. This is the another part, that is radiometric titration, isotopic dilution analysis, IDA, radio immunology assay, RIA, phosphorus 32 post leveling, positron emission tomography, autoradiology, radiography. These things are there. Then on the direct method we have measurement of radionuclide in the system, measurement of stable nuclide. Under this, we have a measurement of natural radioactivity, measure artificial radioactivity, and in measurement of stable nuclide, we have NMR, that is nuclear magnetic resonance spectroscopy is there. Then under indirect, we have another part, activation method, prompt and delayed. Then in the prompt we have these things, and in delayed we have ion beam energy analysis and delay neutron counting. Then radio tester technique, this was invented or discovered by George D. von Hevesy, and for this he awarded Nobel Prize in 1943. Then how to choose radio tracer. It is not possible to use all the nuclide, especially with too long half-life period or too short half-life period, as a radio tracer. Similar type of emitted radiation is also an important criteria. In order to use the radionuclide as tracer, certain assumptions and the criteria have to be met. So the most important assumption is that radio tracers should mix perfectly well with the system under investigation. So to know the concentration or to know the to have the qualitative analysis, we have to add one radioactive nuclide and observe the type of disintegration it undergoes in the same medium. So for this we have to add one radioactive tracer, that is known as radioactive radio tracer, that is that that tracer must not have a too long half-life period or too short half-life period. So we have to choose the tracer very precisely. So it implies that a radio tracer should preferably be in the same chemical form. This is very important. The radio tracer should have the same chemical form. If I go for an investigation of a system with ionic bond, the radio tracer must have the ionic bond. If it is covalent bond, the radio tracer should be a covalent compound. As the analyte with which it is mixed, it means that tracer must have the same behave as an indistinguishable, that means it is same form of the radioactive material that is used for the analysis. Further, it should not be adversely affect any component. This is the general thing, that it should not be react with or have any adverse effect on the system under investigation. Of course, there will be no bond damage. The core stressor is present in small amount, and it is also present like your catalyst. It is just acts as a catalyst. Its presence is very small, but it can carry out the reaction without involving in the reaction. This is very important. Different isotopes of reducer differ in mass between the active and non-active species. So, like note that it is maybe noted there. Substituting hydrogen with deuterium, isotopic mass effect is quite significant, whereas for other elements of higher mass, it will be insignificant. So, if I use the radioactive deuterium in place of hydrogen for any radioactive reaction, then this will not have a significant effect. So these things we have to look after. So what are the factors affecting? So several factors. So just here, final isotope chosen. Before that, we have duration of the experiment, half-life of the isotope. This is very important. That what is the duration of the experiment is depend on the half-life period of the isotope. Then we have, this is just correlate with the compound to be tabled, element of choice and a position within the molecule. Then we have amount of activity per experiment and specific activity available. Then we have physiological consideration, that is the tonicity, radiation effect, concentration, etc. What is tonicity? So let's have tonicity. Tonicity meaning in radioactivity. It is the medical application that it measures the effective osmotic pressure of the gradient. Yes, this is a relative osmotic pressure. So this is related to your osmosis that through a semi-permeable membrane it can allows only the solvent particle, and it will not allow the solute particles to pass through the semi-permeable membrane. This concept is very effective from our surface phenomenon that is related to your sorry, this is very much related to your solution phenomenon, that is Raoult's law, boiling point, a melting point, and there is the concept of osmotic pressure, and this concept is also in your water purifier like in Aquaguard or Kent. Yeah, there is written that RO stands for reverse osmosis. That means the osmosis gets reverse, that it will allow the solute particles. So these things are there. Okay. So tonicity, it is related to osmotic pressure, that is radiation effect and concentration. Then we have availability and cost of the radio tracer. This is very once important. But and accounting facility available, GMs, the Giesel Muller solid state scintillation, radiation type beta or gamma, ease of sample preparation, and these things are the different factors. Then we have the next part, that is isotope dilution analysis. It is widely used quantitative analytical technique of considerable value in complex mixture of compound in organic synthesis, biochemical system, and for the determination of inorganic elements in geological and biological samples. It was first developed by the scientist Hevesi and Hobby in 1932, and the principle is, it is primarily used on the principle that specific activity of a mixture of stable and radioactive remain unchanged during chemical processing. This is the principle that the specific activity of that sample as well as the tracer, radio tracer, will remain unchanged throughout the chemical processing. Accurately known amount of specific activity of a radio tracer is added to an adequate of analyte mixture containing the salt component. After addition, the resultant specific activity decreases. Chemical separation procedure is carried out, but the component need not be recovered quantitatively, but it must be chemically pure from the well-defined composition and is sufficient amount so that it can be weighed. Separation may be carried out by any of the following separation techniques. So here there will be chemical reaction as well as the chemical separation is there, and which is depends on the specific activity of the component. So how this specific activity works, this depends on the activity with the radio tracer. So if there is chemical reaction will happen, there must be a chemical separation. So the chemical separations are solvent extraction process for complex chelate complexes, and we have the precipitation using specific reagents, ion exchange separation, and electrodeposition or sorption. So these separation techniques we have already discussed in our paper 2, that is separation techniques. Then we have specific activity of radio tracer SA plus analyte mixture, that is the sample. It is equal to specific activity of isolated part. So specific activity is defined as, it is activity by mass in milligram. That is activity counts per minute, that is R by M. It is M stands for is mass. So this is the specific activity formula, that is activity of the component with the milligram of the mass, per milligram of the mass. So these things can be the your isotope dilution analysis IDA. So we have two types of isotopes here we are taking, that is M gram and M star. Then we have before mixing we have inactive M1 plus M star is the radio tracer that is active, this is inactive. So after mixing, it will be M1 plus M2. This is the specific activity will change SA1 and SA2. Then this will be the M star of SA1 equal to M1 plus M2 of SA2. That is, these equations are correlated with respect to the specific activity, right? So the left hand side the activity is due to M star, and the right hand side the activity is due to the mixture M1 plus M2. That is M1 plus M star. So M1 will be this one, then percentage will be multiplied by 100. So the radioactive tracer uh, must be radiochemically pure. It must be in pure state. It means that the tracer must not be contaminated with any other radioisotope. This is very important. The radio tracer must be chemically identical. It means that it must be ionic or covalent from the analyte. Form as the analyte. The radio tracer must be uniformly distributed in the sample. It means that the mixture must be stirred thoroughly. Suitable separation procedure must be developed beforehand to isolate the component in pure form. Then half-life of the radio tracer must be sufficiently long so that it should be feasible for chemical reaction. So these things are there. Then we have inverse isotope dilution analysis. That means it gets inverse. So the procedure is also called a direct isotope, that is the first one. In an alternate method, that is inverse method, the amount of radioactive in the sample solution with activity A1 can be determined by adding inactive component M1 and some fraction of the pure component having activity A2. And in this case, M star equal to A1 by A2 M by M minus M1. So here the indirect method is applied for the measurement of the activity. And how to determine the activity of the analyte. We have to add some inactive substances like with the mass M1. Then we have to measure the net activity, and the difference inactivity will be the activity of the sample. Then we have the experimental part here, that a small amount of M star of the radio tracer is added in step 1 with activity SA1, that is activity per mass in milligram, which contain M1 gram of the analyte. Then solution is warmed to make sure of isotopic exchange. Then in the second step, the organic solvent containing a suitable reagent is added. Then after that, two-phase organic solvent mixed is stirred and radio tracer is quantitatively extracted. Then alicate of organic phase is withdrawn on a pipette or in a pipette, then evaporated to dryness. It is step 5. Then after dryness in the plate, we have this is a Geiser-Muller GM plate. Then we have the analysis in GM chamber. What is the specific activity of the radio tracer as well as the specific activity of the unknown sample. Then it is determined through this equation, that is M1, that is mass of analyte. It is equal to activity of A1 by activity of 2 minus 1 into M star. This is the mass of the radio tracer. Okay, so through this method of IDA, and we will able to calculate the mass, the quantitative calculation of the mass of analyte. So these are the different steps, and then we have the instrumentation part. Instrumentation part is there, that use of your GM counter, scintillation gamma ray spectrometer. It can be a good instrument for this detection. We have also um, some applications, that is quantitative isolation of element or compound is difficult, so we can use this method for this determination. Then just go through these examples. Okay, due to paucity of time, I am just skip these things. Just I am just highlighting the main application. This one, the quantitative isolation, more rapid analysis is required. Okay, this is the limitations. Then we have, it is impossible to obtain the entire sample for analysis. So this is the three major drawbacks of this method. Then what are the advantages? In isotope radiation is more sensitive than other analytical method due to application of the radio tracer, which is very much active. So for the elements like zinc, silver, mercury, IDA has better detection limit. Then whether other instrument fails to achieve this limit of complex matrix, IDA appropriately detect. Radio tracer also have potential specificity due to their unique decay property. Quantitative separation is not necessary for the analyte. In many wet chemical analysis involving trace amount, it is almost impossible to achieve quantitative yield. Nuclear detection equipment used IDA are less expensive than many modern techniques. IDA can be used for speciation studies of environmental and biological samples. Decay process of radio tracer is not affected by ambient condition of the temperature, reagent, pH. These have no effect on this disintegration process of radio tracer. So beside this, ID has some limitations. It is a destructive method. The sample is destroyed because this will be reacted with the radio tracer. Uh, then the method can be used for the determination of single element at a time, whereas mixture is not analyzed. It has the applicability of element for the suitable interfaces are available. Then a blank label may vary considerably from 10 to the 6, that is microgram, to picogram 10 to the minus 2 gram. Then we have soft stoichiometric isotope dilution analysis, that is SIDA, SIDA. This is soft stoichiometry means, I think here the radioactive concentration will be half than the concentration of the analyte. It may be. The variation in isotope dilution method was suggested by Ruzicka and Sterry in 1963. The necessary to determine the specific activity makes IDA a difficult technique for trace determination because it is necessary to isolate sufficient weighable amount of substance. This difficulty is overcome by in stoichiometric IDA. So it is difficult to trace determination because it is necessary to isolate sufficient weighable amount of the substance. Yes. So to overcome this problem, this substoichiometry idea is very much effective, where the standard with known amount of analyte, yes, the standard with known amount of analyte and the unknown solutions are subjected to an identical separation process. So here there will be stoichiometric, that is a method, that is a standard solution is prepared with uh, which will be there with the analyte, and unknown solutions are subject to identical or separation. Then we have the test sample here, and there is a mixture here. This mixture is the standard with the analyte, and here this is the sample. So here there is a series of reactions are happening, and there will be the formula, that is m equal to m calculated into activity of 1 by 2 minus mass of the standard m0. Then activation analysis we have, and under this technique we have some nuclear reactions are there induced by neutron, proton or charged particle. Proton, deuterium, deuterons, alpha particle, other heavy metals are produced. That this is generally the a nuclear fission or nuclear fusion type reactions. Okay, activation analysis. Then we have this one. This is a nuclear neutron activation. That is when a target nucleus is bombarded with some neutron, then a daughter nucleus is formed. Okay, which is radioactive, and some subatomic particles are liberated. Here, beta particle is liberated, and in the fast disintegration or bombardment, there is a liberation of your gamma rays. Then we have the equation, that is dnp by dt equal to n sigma uh, tau minus lambda np. So these equations are there. When where the n is the number of target atom, I is the isotopic abundance, sigma is the thermal neutron absorption in bar 10 to minus 24 centimeter square of area. This is psi is the neutron flux, and the lambda is the decay constant, that is 0.693 by T half. This is just obeying the first order kinetics. And we have these equations. Just try to remember these things for your examination point of view. Then we have the next part, and these things are very much not this is so much actually these are complicated parts, and these have some complicated equations are there. This is mono standard method for this equation is here. Then we have some factor, then neutron, where the neutron sources are there, these are the neutron sources. This is photo neutron from yttrium with beryllium 9, or antimony 124 with beryllium 9. We have half-life period of this, average neutron energy in mega electron volt is this, neutron yield is this. So just go through these things. Then we have this is the neutron generator developed by Koch, Roft and Walton. This historical developments, then followed by your thermal NNA, where there is application of heat or temperature. Then epithermal neutron are narrowly defined as having the energy in the range of 0.1 to 1.0 electron volt. Then fast NA neutron activation analysis. This is the widest range that will produce 0.5 to 20 mega electron volt energy. So then there will be interfaces are there in neutron. Uh, uh, it is NNA is based on nuclear phenomenon. Hence, no chemical interfaces are possible. Possible nuclear interfaces are primary, secondary, and second order interface. Gamma ray spectral interface, neutron self shielding, gamma ray self attenuation, true and random coincidences during gamma ray measurement. So these are the things here. Then your sensitivity and detection limit of NAA. Okay, so these are the equations. What is the flux with decay rate? It is given here. Then we have some classification, that is NNA is classified as prompt, derivative, in vivo. Then we have thermal, epithermal, then fast if it is non-destructive. Then this will be of sorry, this fast and in vivo. This is again absolute comparator, and some methods are there. So this is cyclic NNA, INNA, high resolution gamma ray spectroscopy is there. So there, these are the things. Then prompt gamma nuclear activation analysis. In this method, the prompt gamma ray emitted during neutron gamma reaction is illustrated in 13.5. Okay, so where the combination is N and Y, that is neutron gamma, this type of reaction is carried out, then the prompt gamma, that is PGNNA concept, is applicable, which is very much suitable for the determination of lighter elements such as hydrogen, boron, nitrogen, phosphorus, sulfur, carbon, and silicon. Then we have the reactions like this: boron 11 bombarded with neutron to give boron 12 with liberation of or production of gamma. Here the T half is 20.4 microsecond, and this is the energy of the gamma, 4.44 mega electron volt. This is the energy produced during this PGNA analysis. Then short irradiation activation analysis. This is short irradiation, means these have the very short duration, that is 1 to 600 seconds, and this also the same method is applied, that will be boron 11 to boron 12 conversion, and this is also known as fast irradiation measurement system, FIMS. Then we have cyclic neutron activation analysis, that is CNAA. There will be of cycle of transitions or radioactive disintegrations from target 1 to target 2. We have some transitions will be there, and there will be a equations like this. Then we have capital T is the delay period, N is the number of cycle, T small ti is the irradiation time, Tc is the counting time, K is a factor, A is the total cumulative counts per cycle. So this, in this equation, these things are there. Then derivative neutron activation analysis. So this is the differential again, derivative. Okay. So this is also known as molecular activation analysis, which is used to enhance the sensitivity of NNA for more elusive elements. Then we have in vivo. In vivo we have that is used to determine whole body elemental level in living organism. In vivo means this is testing in living organism, that is IVNAA, that is also established in nuclear medicine field, and this is widely applied to biomedical analysis, physiochemical studies, clinical diagnosis, or monitoring of therapeutic intervention of diseases. So this is your proton bombarded with neutron to give deuterium and your gamma ray. So these things are there. Then chemical treatment, we have pre-concentration NAA and chemical neutron activation analysis, which is very much used for the detection of trace metals in water, sedimentary rock, plant, animal, organs, etc. And the pre-concentration NAA, this is useful for the analysis of water sample because of low level of analyte elements, the trace elements in microgram or picogram level. So these things are there. Then speciation neutron activation analysis. This is chief limitations of NA is that it cannot be used for speciation studies. So how its scope can be further extended. Chemical separation of species prior to irradiation and then determine the elemental content. This is essential because of the toxicity of the element depends on its physiochemical form. So the toxicity or the this can be determined by separation of analyte by using liquid chromatography, reverse phase chromatography, ion exchange. So these things can be used for the separation of the different toxic elements from different analyte samples. HPLC also can be used. High performance liquid chromatography, where a low level, that is traces of arsenic 3, arsenic 4 species can be separated. Then we have at the end we have some instrumentation part. So we have Bhabha Atomic Research Center Mumbai have Apsara, Cyrus, Dhruvo, which are used for NAA work. So these nuclear reactors named. India has three nuclear reactors in Bhabha Atomic Research Center, Mumbai, and these reactors are named as Apsara, Cyrus, or Dhruvo. And they have in Bhabha Atomic Research Center there is a separate unit of nuclear department, and this is the high resolution gamma spectroscopy instrumentation. We have just wait. We have a germanium detector, some sensor, preamplifier, amplifier, analog to digital converter ADC is there. Then some computer printers are connected, and through this we will be able to sense the gamma ray emission. then we have then we have some target elements with isotope abundance, product nuclide, apply period, cross sectional area, cross section sigma, and what is the energy produced. Let's have the first example. Aluminum isotope is 27. It is 100% abundance is there. Abundance means availability. Has the half-life period of 2.241 minute. Its cross section is 0.23 and energy 1779 kilo electron volt. So this is the high performance gamma emission spectroscopy, right? Yes. So then we have some plots from there that this is a neem leaf spectrum from your gamma ray spectrum. Then we have this is some from our Opsara reactor of which is in BARC Mumbai. Then calculation of data interpretations are there from through digital mode. Then smoothing of experimental data, peak searching, selection of fitting intervals, peak energy calculation, peak area calculations are automatically done. Then we have some equations for your mm, total peak area. A equal to summation of minus n2 plus n alpha I. It is the cross section minus n plus 1, that is number of neutron, plus 1 by 2 b plus n plus b minus n. So this plus minus sign denotes right and left of the peak channel O, and alpha is the total count in ith channel, and b plus and minus the background count of the 2n. So these are just advanced research techniques, okay? And you are very much fortunate that these things you are just studying, and and this part is not there in any university or any colleges, or even in, I think, in IITs also these things are not there, okay? So this is very specially applied field things, and these are the applications of our in neutron activation analysis. And as I mentioned, ICP-MS, that is inductively coupled plasma mass spectroscopy, or it is X-ray fluorescence, or it is EDXRF. All the things. NA is very much unique, yeah, with respect to these things, because this is very much a precise analysis of the analyte. Then we have NA, the different fields or different areas in which NNA is applied. This will be, this is NAA, okay? So this is archaeological, non-destructive, in forensic, it is blank free, industry, accurate and precise, biology and medicine. This is highly sensitive, environmental, matrix independent, geology, mining, and multi-elemental technique. Then forensic science it is used. Then we have in CFSL, that is Central Forensic Science Lab, Kolkata, and in Analytical Chemistry Division, BARC. This NA technique is used for the determination of the elements like barium, antimony, copper. These things are there. Then environmental studies is also there. That is total suspended particle NP TSP in ambient air of Indian metropolitan cities Delhi, Mumbai, Chennai, Kolkata, Hyderabad, Nagpur. So from these areas, the TSP or it is total suspended solid also TSS. It is also determined through your NAA technique. Then your biological, nutritional, and medical applications are also there. And what are the advantages and limitations? Universally applicability, then virtual absence of any blank or chemical interfaces, high specificity, low detection limit, non-destructive multi-elemental character, radioactive Na through destruction, though destructive, produce interfaces free determination, requirement of only a few milligram amount of sample is needed. Then we have required nuclear reactor which makes it less accessible and cost effective. Long turnaround time, especially for long-lived radionuclides. No information chemical specification is required. Some environmentally important element cannot be determined. It cannot be automated. Only partial automation possible after reaction. These are the limitations. And there is comparison between INAA, RNAA, and IDA for the sample size, accuracy, sensitivity. Just go through these things, and these are the spectroscopic techniques. What are the comparative statements are here? Then followed by your radioactive titration is there. This is the titration part where silver nitrate, silver 110 radioactive silver nitrate is titrated with sodium chloride. It will give a precipitate of silver chloride with sodium nitrate, and this precipitation titration can be carried out through radio titration, right? Radiometric titration, and this is a procedure that it consists of a titration vessel containing filter discs for phase separation, along with the scintillation detector and lead shielding. A syringe is there. This is lead shielding. There will be no radioactive rays coming out to the outer environment. For this, lead shielding is there to shield the radioactive rays coming out from that radioactive decay or radioactive reaction. A syringe is used to move a supernatant solution into and out of the counter cell. So a syringe used, and a typical example is radon titration of halide using silver 110 with T half to 52 days. The tracer corresponding silver halide is precipitated. To understand the method, you may consider the titration of 10 milliliter of 1 millimolar NaCl solution containing chloride with 1 millimolar solution of silver nitrate. So this is the reaction, and this is the solubility product value. So this is the plot between the counter rate from the from this instrument. Okay, radioactive titration experimental setup. From this, we will able to know the counter rate, that is counts per second with the volume of sodium chloride added. We have the slope is from like this. So this will be the equivalence point or endpoint. So some limitations, advantages are there. This method has an advantage that the detection of endpoint doesn't depend on the chemical reaction employed, unlike the normal titration where indicators such as phenolphthalein, methylones are used. In principle, any titration system in which phase separation can be affected is good for radiometric detection. Only phase separation, that is from solution to precipitation. This is enough to know the equivalence point or end point through radiometric titration. Then radiochromatography, this is separation technique again through radio tracers. So like one example is here, this is acid washed asbestos paper, diluted HCl as solvent, radio tracer solution of sodium 22 with T half of 2.6 year and potassium 42 T half of 12.36 hour, then rubidium 86 T half of 18.6 day, cesium having 30.1 year. This can be done through scintillation gamma ray spectrophotometer. And these things are there. Just go through these things. Radioimmunoassays. Assay means this is chemical analysis. The immuno means this is the immune system of human body. That means uh, when tumor cells are detected or cancerous cells are detected in human body, then chemotherapy is done. This chemotherapy is nothing but your radioactivity, that radioactive rays are passing through that cancerous part of your body, and this will destroy the cancerous cells, and this treatment is known as chemotherapy. And for this discovery, this Dr. Rosalind Yalow was awarded Nobel Prize in Medicine in 1977, and where insulin was determined using I-131 as a tracer. So he was discovered because of the detection of insulin by iodine isotope. So this is the principle. Antigen, that is foreign body, antibody production, then antigen, antibody, actually antigen antibody complex. So this complex will sense the presence of your insulin. So here the silver is used, and silver radioactive silver is used, and here this is the antibody. So and this is the antigen, there is a foreign particle. So this will form a complex with some activity. And these are some radioactive methods. Then we have antibody. These are the medical applications. Okay. So antibody radioactive compounds are here. Then 10 units compound. This is radio immunoassay. This one. This is 5 unit of compound to be assayed. 1, 2, 3, 4, 5. Then mix elaborately. So for 5 we have 5. This is a foreign. This is silver, and these are the antibodies. So these antigens are settled on these antibodies, and we have the separation. Are charcoal equilibrate? We will have the separation like this. Decant supernatant liquid. That means this is the separation. There's a medical procedures. Okay, that is mm, that is known as the clinical approach. So these are the antigen count, silver antibody concentration counts. These are the procedure, and then the application part. So much things are there in one unit. So these are the drugs. These are the steroids. Polypeptide hormones are here. Then at the end we have the summary. So this unit is very much very hectic for you guys, and there are a lot of things to be remembered. But I will suggest you just you have to remember the from theoretical exam point of view, this IDA, just you have to go through this IDA and NNA, sorry, NAA, this one, nuclear activation analysis. Just go through these two things and you will have a question. Okay, and some short notes maybe come from your maybe come from radio chromatography, immunology. So these are very much related to your chromatographic method, HPLC, ion exchange chromatography is there. In immunology part, you have the medical or biomedical applications are there. The radiometric titration, there is precipitation, that is silver 110 with sodium nitrate, it will form, sorry, silver nitrate with sodium chloride, it will form silver chloride precipitation, this type of things. And you have to remember this one, the comparison of NaN and IDA. So from this unit, these are the some important from my side, and hope you will get the questions from this part. And this is very much a hectic unit out of all the units, and this is very much just applied part of your radio analytical methods. And hope you will have some knowledge or something that I put in your mind or um, in your knowledge. And hope and anything anyone want to ask or anything want to share, it is now over to you students. And we will have another 5 minutes for any discussion or any query, and after that we will wind up the session. And today is the last session, and hopefully we will meet again in the practical classes, and which may be conducted in the month of September by Regional Center Bhubaneswar. So let's have the schedule to come, and this is over to you. And anyone asks anything to share or anything, so you may. So if no questions are there, so thank you from ignoring.
Sir, am I? Hello.
Yes, 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 Mahendra Sahu. Yes, yes, yes,
Sir, I have some question
yes,
related to this exam. Sir, before our theoretical exam, we have to submit the assignment. Suppose
yes.
I am preparing for the next year June month for the theoretical exam. For that case, when I have to submit the assignment.
So the assignment submission, there is no time bound. Okay, so you just submit your assignment as per the stipulated deadline, and
Yes.
what, and it is on you that when you will appear the examination. So examination and assignment both are two different things.
Okay, sir. Sir,
Okay.
another thing. So, sir.
So just wait, Mahendra. Are you belong to Odisha?
Okay. Yes, sir.
So you may talk to me in Odia language. It is more
Okay, sir.
it is more convenient to both of us. Okay.
Okay, okay.
Mm.
ସାର୍
କୁହନ୍ତୁ।
କହୁଥିଲି ଯଦି ସାର୍ ଚାରିଟା ୟୁନିଟ୍ ଅଛି,
ହୁଁ
ଚାରିଟା ୟୁନିଟ୍ରୁ ଏଇ ଡିସେମ୍ବରରେ ଯଦି ଦିଟା ୟୁନିଟ୍ ପାଇଁ ଏକ୍ଜାମ୍ ଦେଲି,
ହୁଁ
ନେକ୍ସଟ ଜୁନରେ ଯଦି ଦିଟା ୟୁନିଟ୍ ଦେଲି, ଏମିତି କ'ଣ କରିହବ?
କରିହବ, କିଛି ଅସୁବିଧା ନାହିଁ। ଯେତେବେଳେ ତମେ ଫର୍ମ ଫିଲ୍ଅପ୍ କରିବ,
ହଁ
ସେତେବେଳେ ତମେ
ହଁ
ପେପର ଚୁଜ୍ କରିବ। ଚାରିଟା ପେପର ଆସିବ, ତମେ ଯୋଉ
ହଁ
ଦିଟା
ହଁ
ପେପର ଦବ ସେଇ ଦିଟା ପେପର ଚୁଜ୍ କରିବ। ପର ପେପର ଆଇ ଥିଙ୍କ 200 rupees ତାର ଏକ୍ସାମିନେସନ ଫି ଅଛି। ତମେ
ହଁ
400 rupees ଅନଲାଇନ୍ ପେମେଣ୍ଟ କଲେ ତମର ସେଇ ଦିଟା ଏକ୍ସାମ୍ ଯୋଉ ଡେଟ୍ରେ ଥିବ ତମେ ସେ ଡେଟ୍ରେ ଦେବ।
ଆଉ ତାହେଲେ ସାର୍ ସେଇ ଆକର୍ଡିଂ ଟୁ ପେପର ଅନୁସାରେ ପ୍ରାକ୍ଟିକାଲ ଏକ୍ଜାମଟା ଦେବି ନା କ'ଣ ସାର୍?
ନା
ନା
ପ୍ରାକ୍ଟିକାଲ ଏକ୍ସାମ୍ ସେଟା ପୁଣି ଆଉ ଗୋଟେ ଡିଫରେଣ୍ଟ ଥିଙ୍ଗ। ଆସାଇନମେଣ୍ଟ, ଥିଓରି, ପ୍ରାକ୍ଟିକାଲ, ଦିସ୍ ଥ୍ରୀ ଆର୍ ଥ୍ରୀ ଡିଫରେଣ୍ଟ ଥିଙ୍ଗସ୍। ଆପଣ
ଓକେ
ସବୁ
ସାର୍ ଓକେ
ମିକ୍ସ କରନ୍ତୁନି ହେଲା। ଆଉ ଯେତେବେଳେ
ହଁ ହଁ
ଆପଣଙ୍କର
ହଁ
ମନେ ରଖନ୍ତୁ ଯେ ଫର୍ PGDSC program 2023-24 session there will be
ହଁ
one practical examination, and
ହଉ ହଉ
you will check your mail periodically to get the
ହଁ
information, so when and where your practical examination is to be held.
ସାର୍
Hmm.
ସାର୍ଟିଫିକେଟ ଯେତେବେଳେ ଆସିବ, ଏଇ ଯୋଉ ହଉଛି ଥରାକର କମ୍ପ୍ଲିଟ ନ କରିକି ଏଇ ଯୋଉ ଦି ଥର କରିକି ଡିଲେ କରିକି ଦେଲି ସାର୍ଟିଫିକେଟ ର କି ମେନସନ ଥିବ ମାନେ
ନାଇଁ ନାଇଁ
ସପ୍ଲିମେଣ୍ଟାରୀ
ମେନସନ କେବଳ ସାର୍ଟିଫିକେଟ ରେ the certificate will be written as you have completed this program in this session, that is January 2024 or December 2024. These things only written. Nothing is written
थैंक
that
यू सर
this paper is attempted thrice, twice, or once. This type of things not written. Okay.
थैंक यू सर ଏଇଟା
Okay.
ଟିକେ ଡାଉଟ୍ ଥିଲା ସାର୍
ନାଇଁ କିଛି ପ୍ରୋବ୍ଲେମ୍ ଓକେ ଓକେ କିନ୍ତୁ
ଓକେ
ପିଲାମାନେ so I suggest you all do not miss the practical classes as well as the practical exam which will be conducted once for your batch. So last year we have intimated around 90 plus students of PGDSE program, but only around 25 to 30 students appeared the exam online. So the rest 60 to 70 students got failed in the examination, because if you do not pass all the papers or clear all the papers, then your program is not be completed. Mind it. So you have to clear all the theory papers, assignments, and your 4 practicals. Each paper is important for this program. Each paper is important, so do not miss, and always keep your email active, keep your mobile number active. At any time or any day you will have the mail from regional center or from Delhi, IGNO Delhi. Okay.
हेलो हेलो
ओके
सर
सर ओके
Okay, one by one. Rajasmita Misra.
ଆଜ୍ଞା ସାର୍ 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 ଆକ୍ଚୁଆଲି ମୁଁ ଜୁଲାଇ 2022ରେ ମୁଁ ଆଡ଼ମିସନ୍ କରିଥିଲି।
Hmm.
ତ ମୁଁ ମାନେ ଆସାଇନମେଣ୍ଟ ଅଲରେଡ଼ି ସବମିଟ୍ କରିଦେଇଛି ଡିସେମ୍ବର ମନ୍ଥ 2022ରେ। ତ ମୋତେ ଆଉ ଆସାଇନମେଣ୍ଟ ଆଉଥରେ କିଛି ଲେଖିବାର ଅଛି କି ସାର୍?
No, no, no. You will submit the assignment once for a
ଓକେ
particular program and for a
ସାର୍
particular paper. So
ଓକେ ସାର୍
only one assignment for one paper for one program. There will be no second time option to deposit or submit the assignment again. Okay.
ସାର୍ ଆଉ ଗୋଟେ କଥା ସାର୍ ଆକ୍ଚୁଆଲି ଇଏ ଜୁନ୍ ମନ୍ଥରେ ମୁଁ ଥିଓରି ଏକ୍ଜାମ୍ ପ୍ରାକ୍ଟିକାଲ ଏକ୍ଜାମ୍ ଦୁଇଟାକ ଅଲରେଡ଼ି ମାନେ ଆପ୍ଲାଏ କରିଥିଲି। ତ ଏମିତି ମୁଁ ଜାଣିନଥିଲି ଯେ ଏମିତି ଦିଟା ଏମିତି ତମେ ଡିଷ୍ଟାନ୍ସ ମାନେ ଗ୍ୟାପ୍ ଦେଇ ବି ଏକ୍ଜାମ୍ ଦେଇପାରିବ, ଏମିତି ମୁଁ ଜାଣିନଥିଲି ଏମିତି ପ୍ରୋସେସ୍ ଅଛି ବୋଲି ଇଗ୍ନୋରେ। ତ ମୁଁ ଆଟ୍ ଏ ଟାଇମ୍ ମୁଁ 4ଟା ଥିଓରି 4ଟା ପ୍ରାକ୍ଟିକାଲ ମାନେ ଫର୍ମ ଫିଲ୍ଅପ୍ କରିଦେଇଥିଲି।
Practical ର
ତ
form fill up କରିଥିବ, କାରଣ practical form fill up ତ ନାହିଁ, କେବଳ theory ର ଅଛି। Practical ହଉଛି
ଆଜ୍ଞା
ତୁମର
ତ ମୁଁ ମାନେ ପଇସା ବି ଦେଇଦେଇଛି ତ 200 ଏମିତି 800-1600 ଟଙ୍କା ଦେଇକି ମୁଁ ଦିଟା ଥିଓରି ପ୍ରାକ୍ଟିକାଲ
practical actually, as far as I know, or as far as my knowledge is concerned, there will be
ଆଜ୍ଞା
no payment of your practical examination. Only you have to pay for the theoretical examination, and it depends on the study center to which you are opted for.
ନାଇଁ ସେ ଇଏରେ ବି ଲେଖା ହେଇଥିଲା ମାନେ ଥିଓରି ପାଇଁ 200, 4ଟା ଥିଓରି ପାଇଁ 200x4, ପ୍ରାକ୍ଟିକାଲ ପାଇଁ 200x4।
So any other students will who face the same situation, that you have to pay 4 into 200 for theory paper as well as 4 into 200 for practical paper. Anyone who submit the examination form? Okay, it's okay, Rajasmita. So
ଆଜ୍ଞା ସାର୍
Hello,
let's
sir.
let's
Hello.
have the time to come. Okay, so Abrar.
Hello.
ଆଜ୍ଞା
Hello.
Yes, Abrar, please.
Sir, only for theoretical papers are fee, not for practicals.
I do not understand your question. Are you from Bengal, Kolkata?
नहीं सर, आई एम फ्रॉम जम्मू कश्मीर.
So you may speak in Hindi.
यस सर.
Okay. Ask.
सर मैंने बोला है कि थ्योरेटिकल के लिए ओनली पे करना पड़ता है, प्रैक्टिकल के लिए कोई पे नहीं करनी पड़ती है.
Yes. That's the thing I want to say, that there will be no payment for practical.
यस सर. सर मैं ये जानना चाहता हूँ कि प्रैक्टिकल के क्लासेस कब शुरू होंगे.
You will get mail from the respective IGNO regional centers on that will conduct that one. Okay, the practical. You will just check your mail periodically.
सर.
Yes.
सर.
Hmm.
सर मैं ये कहना चाहता हूँ कि फिर भी कोई इंफॉर्मेशन होगी आपके रीजनल सेंटर को.
If any information or is any finalization of the date of that your practical classes or practical examination, I will put message in your WhatsApp. Okay.
सर ये तो पता होगा कि ऑनलाइन ही होंगे क्लासेस.
Online classes will be online, and it depends on the time on which the practical examination will be held. So classes will be online. Okay.
एग्जाम.
Exam, it depends. It depends.
It depends.
At which situation, if corona came, then it will be online. If your Delhi head office decide that the examination, practical examination will be online or offline, this will depend on your
सर. सर एक बात है ना, मैं जो मेरा रीजनल सेंटर है उसमें खाली ओनली वन स्टूडेंट एंड फॉर मी.
हाँ. ओके. हाँ.
मैं अकेला हूँ उस रीजनल सेंटर में, मैं अकेला हूँ इस प्रोग्राम के लिए.
नहीं ठीक है, वो कुछ बात नहीं. बस अभी इसके बाद आप प्रैक्टिकल क्लास करो ऑनलाइन में, फिर प्रैक्टिकल एग्जाम जो होगा उसके बाद उसका शेड्यूल निकलेगा. डू नॉट वरी अबाउट दैट. ओके.
ओके थैंक यू.
And as from last 3 to 4 years, the practical examinations are conducted online. Only you have to face, you have to just wait.
Sir, you are a group admin in PGDA program. You only all share information is.
Yes.
In other students.
I will share. I will add the directors or coordinators from regional center Bhubaneswar. Then they have the information about the students. I do not have the information. I do not have the numbers. Okay. So if any information come to me from regional center regarding your program, I will put messages in your WhatsApp. Do not worry.
Thank you, sir. Thank you, sir. Thank you, sir.
Okay.
Thank you, sir.
Anything else from anyone? Ojas Dhamapurkar. You put a nice nice information that the Apsara reactor is now in the museum for people. This is the latest updation regarding your Apsara reactor in BARC Mumbai, Atom Research Center, and I will ask Ojas to say something over that. How, in which place or where is this museum is located, in BRC or in any other places. Ojas, are you hearing me? Actually, he might be not here. Okay, so any student, anything you wish to ask or share, you may ask, or else we will wind up the session. So okay, so thank you to all for your patience hearing and patience. Yes, Ojas.
Yeah, sorry. Yeah, I got disconnected. Yeah, sir, you were asking something.
Okay. Yes, Ojas.
Yeah, sir, you were asking something, right? About
yes. My query is, you have put a message in the chat box that the Apsara reactor is now in the museum. So just
sir, no, sir. Actually, the news came this month only that they are making it a museum because in 2009 they decommissioned it, and in 2018 they again started it. So after that, now they are planning to make it a museum for display because
Okay,
anyways they
okay.
are using it for research purpose only.
Yeah, actually, this technology is now very old, and new technologies are came up. So that's why this might be absurd now, Apsara reactor, and this will be
Yes,
the museum for the peoples. It is a good information.
yes,
Okay,
yes.
thank you, thank you, thank you.
Okay.
So
Thank you, sir.
are you staying in Mumbai?
Yes, sir. Yes,
Okay, where in Mumbai?
sir. I actually stay in Thane. Means it's a suburb in Mumbai.
Yes, yes, I know. There's Thane West or East?
Thane East.
East. That is near, I think, ACC Cement is there, or ACC Cement is in West. West, I
Sir.
think. Yes, yes, yes. Okay. So, anyone, anything want to share or something to say, because this is the last day of our class, and I have got good experience with you, with people like you. You are very much obedient. You are the 12th number of students who are regularly attended my class, and I feel very much privileged, and I would like to put my gratitude to all of you, that you all are participate very sincerely, and put your best effort to make these 7 day classes effective and fruitful, and hope this cooperation will go on, and I wish all the best to all of you, and I pray God for you for your successful completion of this program. So thank you to all.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir. Thank you.
Thank you, sir.
Thank you, sir.